Good morning, everyone. So thanks for joining us for this webinar on fan-powered chilled water terminals. It's our no sweat and sound solution. Little play on words. We're going to go ahead and start. I'd like to introduce Mark Mann. He's the product specialist for air moving products from Price Industries.
Thanks, Jake. And thank you everyone for joining in. Today we're talking about series fan-powered chilled water terminals. And, what we're really going to look at is maybe defining these products a little bit better and talking about some of the specific ways to apply them to take advantage of them as an air distribution system. DOAS has become so popular due to its ability to provide, better ventilation, better occupant comfort, and energy efficiency. But the way that it's applied, there's so many different variations, whether it's a chilled beam setup or whether it's this fan-powered chilled water terminal. And understanding the downstream air distribution side has very significant impacts on the performance of the system, and understanding how to kind of apply some of the unique configurations here can lead to better design. So as a bit of an intro here, a bit of a review and very quick, why does DOAS actually work? It really comes down to the fact that in comparison to traditional VAV, which puts all of the responsibilities of the system into air only, latent cooling, sensible cooling, and ventilation, when we look at DOAS and the decoupling of responsibilities between air and water, that really just leads to a more efficient system overall. We have latent and fresh air being handled by primary, and we have water handling sensible cooling only. And really, the biggest reason why this works so well is that decoupling, which means both sides can kind of be balanced and selected a bit more efficiently. The other major reason why is because of water's volumetric heat capacity, which is 3,500 times higher than that of air at sea level. And what that really means is an 18 by 18 inch traditional VAV duct, like we see on the left-hand side of the screen, carries the same capacity as a 7-inch round duct and 1-inch water pipe in a dedicated outdoor air system. So looking specifically at the product we're discussing today, the fan-powered terminal unit, the fan-powered chilled water terminal unit being integrated in this kind of a system, why is it such a perfect fit for this dedicated outdoor air system kind of layout? Well, all of the components are handled very effectively through this downstream air distribution solution. We have the primary air valve, which can maintain flow of ventilation air to meet the latent load and to provide enough fresh air for breathing. And we have that cross flow sensor, so we're going to be able to get really quality airflow measurement, and we're going to be able to modulate that airflow with a butterfly damper. The sensible cooling coil handles space sensible dry cooling loads. And it does that very, very effectively, considering how large that coil can be, generally selected at 6 or 8 rows of coil depth and a very, very large coil face area. And then the last piece there is that ECM fan, which is accounting for all downstream pressure requirements. It's accounting for air pressure drop as well through filters and through the sensible coil. So really all components of air distribution for a DOAS system is handled by this box. The real reason also why we're reaching out to you and wanting to talk to you about this equipment right now is because there's been some considerable industry improvements happening recently in the last, let's say, 12 to 18 months. When we look on the left-hand side of the screen, that's the Price FDC LP2 DOAS box, the low-profile version. And on the right, we have the new standard height FDC DOAS. For those of you who, maybe aren't familiar with the history of this equipment, it was actually originally established and created for the Washington, D.C. region, which has some really strict building codes, especially in regards to building height. Nothing can be taller than the Washington Monument. So that results in a minimized floor to ceiling height and a minimized plenum height. And essentially the original piece of equipment, the low profile box on the left, was created for that market with the intent of a series fan-powered layout with chilled beam efficiency and performance. So Price Industries is the first to market with a standard height offering, which we can see on the right-hand side of the screen there. So increasing the 11-inch casing height up to an 18.5 to 20 1/8 inch casing height. And the real benefit and why is this such an improvement? Well, a larger casing height results in much higher airflow ranges. It's also going to result in a much larger max coil face area. So a taller coil without sacrificing too much width on that coil face. And the result there is much more sensible coil capacity, which can be delivered to the space. So this means that equipment can be consolidated for value engineering and cost improvements for projects. It also means that zones with high loads can have at many times one piece of equipment or a piece of equipment that can operate much more quietly, because as we reduce the footprint of the equipment and bring up the height, generally the sound power at matched CFMs tends to improve significantly. So looking a little bit deeper here, what are some of the benefits of a fan-powered terminal in a dedicated outdoor air system specifically? Well, the first one is the fact that humidity control is independent of thermal conditions. So we have that dry bulb temperature fully being taken care of by our sensible cooling coil. And then we have our fresh air and our latent load being taken care of by that outdoor air going through the primary air valve. And those two volumes are completely independent of each other. So we can vary the volume of primary air, or we can vary the amount of airflow going through that equipment's coil fully independently of one another. Additionally, a large benefit is the utilization of a cross-flow sensor and damper on the fresh air inlet enables monitoring and control of fresh air. So this also leads to demand control ventilation and the discussion of providing and kind of adding in some extra efficiency of only providing the ventilation air required by the zone. And so that's really only possible because of that damper, which can vary that fresh air and monitor that fresh air. Having that EC motor is also a huge advantage. So that fan is going to allow for morning warm-up and night setback, which, for instance, with a chilled beam system, you would either need some kind of inline fan system, or you would have to have the air handler running to kind of heat the space up potentially in the morning if it was a chilled beam only system. As well, fan operation reduces zone stratification and improves indoor air quality. So when we're looking at temperature deadband, we can keep that fan generally running quite high, even when we look at Washington State Energy Code and 0.12 watts per CFM, we can keep those airflows quite high, which is going to mean that the zone is going to be less stratified. In the actual occupant zone, in the breathing zone, we're going to find the temperature there is going to be, realistic for what the thermostat's reading. And our improved indoor air quality is also another major consideration. So any ventilation air which is exhausted out of the space into the plenum that's not actually breathed by occupants is going to get recirculated through the coil and pushed back into the room. That fan motor is also accounting for all downstream static pressure and allowing for more diverse outlet options. So whether you're wanting to wash windows with slots or do any different kind of typical air distribution, air outlet configuration, all of those options are available with this piece of equipment above the ceiling. And then last, there's also less piece of equipment and it's easier to install. So for instance, when we look at comparing this equipment to chilled beams, the largest piece of equipment can essentially be consolidating maybe somewhere between 30 and 40 linear feet of 24-inch active chilled beam. So what that really means is just less equipment to install and maintain within the space. So the next thing I want to look at here is the managing of reheat options and some of the unique things we do at Price, which can be an asset when selecting this equipment. So there's lots of different possible ways to be reheating equipment or reheating air with this equipment, whether that's, the typical hot water coil on the discharge, whether that's an electric coil on the discharge, or whether that's even utilizing a hot water coil on the return of the unit. And that can be an additional coil accessory kind of sitting outside of the sensible cooling coil or inside the sensible cooling coil as well. Either is an option. Or it could be potentially a hot cold changeover application, which would be far less common, but definitely something we can offer. And there's lots of considerations when you're looking at selecting this reheat. So for instance, the first would be air pressure drop. And when we look at air pressure drop and we look at energy efficiency, the less resistance to airflow we can provide in the ductwork with our equipment, the more efficient our system is going to be overall. So when we look at an electric coil, an open wire electric reheat coil has very negligible pressure drop. So that's kind of maybe the optimal selection in terms of pressure drop. However, there's other benefits as well, such as, if we have a return coil, which is going to have a much larger coil face area. Sorry about that puppy in the background here. If we look at a return reheat coil with a much larger coil face area, that's going to result in a much lower air pressure drop than, for instance, a discharge coil downstream of the equipment. Another major consideration here would be the entering water temperature. So for instance, a larger coil face area is going to be a very large benefit if you have a much lower entering water temperature for heating. So I generally like to say, if you're kind of looking at 130, 140 Fahrenheit and down, there's some tangible benefit to being able to be offered a return configuration reheat coil. If you're looking at higher entering water temperatures, 160 or 180 degrees, you might be looking at and requiring a smaller coil area in order to get the leaving water temperatures you're wanting. So maybe in that case, you go for a discharge configuration. And then finally, and kind of obviously as well, what are your capacity requirements? And because the larger the water coil you can offer, the higher the potential capacity available. Looking beyond this, when you're looking at reheat options, there's the discussion of packaging the solution. And at Price, we can offer a factory mounted valve package on this piece of equipment or any other. We can actually see on the right-hand side of the screen that's a shipment of this product actually leaving the Price factory with factory mounted valve packages mounted on it. This is a big discussion point in the industry as well. It's been a big kind of product release for Price in the last year. And it's because it leads to lots of cost and time savings in the field. And when you're looking at a piece of equipment that can potentially have, 4 water connections, being able to eliminate some of that field labor can be a real asset. Generally, when we look at our assemblies, contractors are saying that it often is saving 1 to 1.5 hours of field labor per 2-pipe assembly in the field. So if you're looking at sensible cooling and reheat on this equipment, getting a Price factory mounted valve package could save 2 to 3 hours of field labor per assembly, which looking at the size of some projects is going to add up and create some considerable, value for a project. Another major component of this equipment, which I think is maybe a little bit undervalued or overlooked, but Price takes very seriously, is sound. So when we look at a fan-powered chilled water terminal, there's 2 sound sources. There's our primary air damper, and the sound emitted from that source is dependent and fluctuating with respect to the pressure drop across the primary air valve, and then also the volume of air across that air valve. And then there's also the motor and blower assembly. And that sound emitted is dependent on where the fan is operating within the fan curve. Now, the major consideration for this equipment and the real importance of this equipment, which I think gets overlooked, is the fact that for all intents and purposes, this equipment has a large hole in the side of it, which is leaking that valve noise and that fan noise out of the equipment and into the plenum. And because of this, at Price, we've looked into many different ways of trying to find the best solution to kind of mitigate, especially radiated noise for this equipment. And we settled on what we call our close-coupled return inlet silencer, or our RSLR, which is essentially a sound trap that fits downstream of the water coil and kind of is sandwiched in between that water coil and that motor blower and primary air valve. The real importance of this in application is in those open ceiling radiated sound applications. So if you have an open office, or you have a school and this is in a corridor, or anything in between there, this is kind of in many ways a mandatory option. We see it engineered out and we see it added back into projects frequently. It's not that this equipment can't be quiet in a solution, because it certainly can. For instance, I've seen it applied with success in schools and even in inpatient hospitals. We had a few large projects with that last year. But in sound sensitive spaces, being able to upsize the box and provide this as a targeted sound solution is critical, and it's not something that every manufacturer can offer. The other key consideration is, where we choose to mount our silencer. We have both a 1 foot and a 3 foot silencer option. And as I stated, we mount this in between the water coil and the piece of equipment. This is really critical because of the way that coils are tested on these pieces of equipment. So our coils are tested as per ACI 410. And ACI 410 essentially takes that coil and treats it as its own certified separate accessory. So that coil is mounted in a piece of uniform straight duct, and that ductwork has very equal airflow across it and pretty optimal condition. And that would be certified separately from any sound trap or any silencer that would be mounted in front of or behind it. So with that in mind, you could imagine if you have a silencer that's kind of restricting coil face, that's going to lead to a smaller effective coil face and localized velocity. That's the major consideration for why we choose to mount our silencer in between the equipment and after the coil. That's to keep that localized velocity across that coil and to maintain capacity that you expect, and that wouldn't show up and change performance were the silencer mounted in front of the coil. So another point of discussion here, just a little bit of quick education. If we look at sequencing of this equipment, I think this is a little understood, or it's at least some good background if this is a newer piece of equipment for you. When we look at the cooling side of sequencing, beyond deadband, the first thing that generally happens is the opening of a sensible chilled water valve. So that's generally the first stage of cooling there, whereas the second stage of cooling would be the engaging of a fan and actually the increase in fan airflow. Now, the main reason for that is kind of seen when we mirror it on the opposite side and look at heating. The first stage of heating is actually keeping a heating valve closed, but increasing that fan output or turning up that fan airflow. This fan airflow, if the coils are not being utilized, is essentially just air which is being induced from the plenum, which is expected to be somewhere in that range of 75, 62 degree design day kind of plenum air. So if we're increasing that fan and if we're not sensibly cooling it with a coil, it's actually going to be helping to deliver that warm, sealing air back down into the occupied zone. And it's actually kind of like a free stage of reheat. Because of that, when we look at a second stage of heating, that's opening up that heating valve or turning on that staged electric heat. On the cooling side, on the opposite side, we're always going to be engaging that fluid side previously in kind of as a first stage before increasing the fan output. One other important note here, generally on sequence diagrams, we would see some kind of primary airflow discussion. And I've kind of left it blank here as an intentional transition point to just look at demand control ventilation a little bit further and kind of just to paint the picture and communicate that this is such a perfect kind of bread and butter cherry on top type of solution when you look at series fan powered chilled water terminals applied within dedicated outdoor air system. So demand control ventilation control strategies fit very, very well within dedicated outdoor air systems. Fresh air is just brought through that primary air valve and controlled based on generally a carbon dioxide, level within the occupied space, although there are occupancy sensors similar to what would be used in like a Nest home thermostat that are becoming more prevalent and working really well. And this is a fantastic example and something that should be utilized frequently. Demand control ventilation, there's lots of different ways that this strategy works. The most common example of it would be through carbon dioxide detection specifically. And I do actually have an example of that, which I'll pass on afterwards to circulate to you guys, that we have an example of with some slides that I'm actually going to glance over for time here so we can get to some questions. So the last thing I want to show before we have a question period would be specifically looking at maybe laying out some performance schedules, which is something that ACI and Price are happy to help with in the design stage of this kind of equipment. So it's a major pitfall with this equipment, kind of the misunderstanding of sensible capacity calculations. If we see below, we have this table here. This is often the kind of table that I'd be seeing with this kind of equipment provided. So the typical kind of performance and equipment schedule. And it would have a cooling coil section with a capacity called out. Now, it's not always communicated what this capacity is actually based on. I see, sometimes when you go through and try to pick out and do some hand calculations to kind of garner some more understanding on the schedule, sometimes I see this capacity is based on a fan CFM running through the coil, which is unrealistic. Sometimes you see that this max cooling coil capacity is a coil CFM, so a fan CFM minus an outdoor air maximum CFM, which we'll look at in the next slide. And then sometimes we see that this would be a coil CFM and then also a primary sensible boost. So for those familiar with chilled beam systems, this would be kind of a chilled beam type sensible capacity. So the reason why these things get confused and conflated is because of the way this equipment operates. As the primary air changes and the fan air is held constant, the amount of airflow going through this coil also changes. So that's why it's a bit of a misnomer or a little bit incorrect when, at times we'd see this capacity here calculated with respect to the fan flow that's operating. So an assumption of 1600 CFM through this coil would be incorrect, while an assumption of 1600 less 400 or 1200 CFM through this coil would be much more optimal and ideal. So how would we actually recommend to calculate sensible capacity? Well, what we'd really like to look at is a coil sensible capacity being called out, as well as a primary sensible capacity being called out, and then a total sensible capacity being called out as well. The combination of these together is going to lead to the most understanding on the schedule. It's going to simplify it as much as possible, and it's going to make it very clear just to make sure that people don't provide undersized or oversized equipment.
Thank you very much, Mark. Really appreciate all the information. We do have a question here from John Taylor. I see it here in the questions section. How does the operation compare energy-wise to a system that is able to have 100% economizer?
Yeah, that's an interesting question, and not one that necessarily we've done, for instance, like a study on or something like that. I think generally, when people look at this equipment and kind of DOAS equipment, I think it mostly gets compared to chilled beams specifically, or it gets compared to a VAV system. I'll have to look into that, and I'll reach out through Jake and try to pass on some further insight and info and speak to that a little bit more if I can. But I'd have to see maybe what the industry research has been on that.
Got it. Thanks, Mark. Brian Butler here asks, will Price factory mount any DDC vendors control valve on their terminal units?
Yeah, that's a great question. So we will factory mount any VAV controller or any temperature control valve for the hydronic side as well. We are aware that frequently the kind of valve body supporting valves are very much part of the mechanical bid, whereas it's more of the control contractor's bid to provide the temperature control valve or DDC controls. So that's always something that we facilitate, and that's probably most frequent. What we see, we either see field mounted or we'll see factory mounted TCV and or DDC.
Linda Berman asks, if you connect a DOAS unit to the chilled water system, is that true separation of systems as far as the energy code is concerned? Does the chilled water stop flowing in straight outside air mode? And what if the chiller is serving several zones?
Yeah, that's a good question. I think that's maybe something me and Brian will have to touch base on, because some of the nuance of Washington State Energy Code and Oregon Energy Code is not as much my domain. Generally, you don't have these boxes operate up to a fully maximized outdoor air only, which I think was part of the question, if I heard it correctly. If not, please follow up. Usually, if you're trying to control latent load, you might size the primary air valve a little bit higher than minimum ventilation. But usually you'd have the chilled water operating kind of in its own sequencing from the primary air, and then the primary air would be dealing with latent load as it's required. And usually you'd set the dew point temperature of that outdoor air to handle the latent load with the ventilation requirement of the zone.
Mark, I'll add on to that. So Brian Wolford with ACI VP of Engineering. So to answer a little bit more of Linda's question there. So heating and cooling, yes, water flows. When it's in deadband, water shuts off to that coil. Heating and cooling, that water shuts off. The next part that meets Washington State Energy Code is we actually will back that fan down to under the threshold of the 0.12 watts per CFM, which Mark has kindly given us some charts on what that threshold is. So that's how that meets the Washington State Energy Code. Heating, cooling, chilled water in deadband, that water shuts off, fan pulls back to under 0.12 watts of CFM. One other thing that I do like about the system is that threshold of 0.12 watts per CFM. The CFM is actually still fairly high, as in like we're not seeing a significant turn down, so you don't get that occupant sensation of a rush of air turning on and off. You're still engaging the diffusers, you're still rolling the room, engaging the thermostat. So that's another side benefit to this system.
Thank you, Brian. Bart Warrington asks, with a 12-inch sound trap, what is the spacing between the actual trap inlet and the induced air coil? And then how are you able to account for the full area of the coil, unlike our competition?
Yeah, that's a great question. So the coil, and like there essentially be a clearance of a couple inches just the way it's mounted, but it's essentially a flush mounting. And the way that we get around that from a sound purpose, just because generally sound traps would be measured with significant straight upstream and downstream duct in order to fully capture the insertion loss of that sound trap. we actually test the whole thing as an assembly. So we test, you know, specifically the sound trap as a part of the assembly, and we find the sound reduction from that. So that's how we can kind of quantify it with a higher level of accuracy. And the same thing goes for the capacity side. So we've done some testing to verify which coil position would result in kind of the best sound performance and the best capacity performance as well. So we've done spot checks through our range with kind of more of a 440 AHRI test with the silencer mounted upstream and downstream of that coil. And we found that the coil was impacted more in that 440 test with the silencer mounted upstream. When it was mounted downstream, I guess you get more of that coil face utilization from the airflow just coming straight from the plenum. And it would have to kind of break out to go around sound baffles afterwards, but the impact of it was much less significant.
Thank you, Mark. That's great. Thank you all for